Genevieve speaking. In this presentation, we'll go over the methods used to conduct hypothesis tests. First, we'll go over how to develop our null and alternative hypothesis. Second, we'll go over what type 1 and type 2 errors are. Next, we'll go over the method or steps to follow to conduct a hypothesis test, distinguishing between one-tailed and two-tailed tests, pointing out the relationship between hypothesis testing and interval estimation, highlighting the changes in our method when the population standard deviation is unknown, and addressing the hypothesis test around a population proportion as opposed to a population mean. First, let's develop our null and alternative hypothesis. HA, sometimes called H1, is our alternative hypothesis because it is the opposite of what is stated in the null hypothesis H0. In many cases, HA is our research hypothesis. That's the one we hoped to support. For example, our research hypothesis could be beef pot roast made by Morel is the preferred choice of more than 50% of the consumer population. Once we've identified our research or alternative hypothesis, we can develop our null hypothesis. The null and alternative hypotheses are opposite of one another. Because our alternative hypothesis is the proportion is greater than 0.5, the null hypothesis, opposite of that, is that the proportion is less than or equal to 0.5. If the sample data support rejecting the null hypothesis H0 in favor of the alternative hypothesis HA, then we can conclude the beef pot roast made by Morel is the preferred choice by more than 50% of the consumer population. If the sample data does not support rejecting the null hypothesis, then we conclude we have no statistical evidence to support the hypothesis that beef pot roast made by Morel is the preferred choice by more than 50% of the consumer population. So we have no statistical evidence to support our alternative hypothesis because we were not able to reject our null. But when we are not able to reject our null, we cannot say either that we have evidence that our null hypothesis is true either. We can say perhaps more research and further testing can be conducted. It is always the case that HA and H0 or H0 and HA are opposite of one another. We just looked at an example where HA was our research hypothesis, and in such cases, we saw it was easier to first identify HA and then develop H0. Let's now look at a case where the null hypothesis is the assumption to be challenged. In this type of situations, it is helpful to develop the null hypothesis first. As an example, let's consider the situation of a manufacturer of soft drink products. The label on a soft drink can states it contains 12 fluid ounces. We consider the label correct, provided the population mean filling weight for the cans is at least 12 fluid ounces. So we start by specifying our null hypothesis to be just that. The challenge to this assumption would imply that the label is incorrect and the cans are being underfilled. This would be our alternative hypothesis. If the sample data support rejecting the null hypothesis in favor of the alternative one, then we can conclude the label is incorrect and underfilling of the cans is occurring. If the sample data does not support rejecting the null hypothesis, then we conclude just that the assumption that the manufacturer's labeling is correct cannot be rejected. Remember, when we are not able to reject our null hypothesis, we cannot say that we have evidence it is true either. Let's now consider a variation of the soft drink example. The production process has been designed to fill the cans with 12 fluid ounces, as stated on the label, so the company does not want to underfill the containers to avoid customers' complaints, but doesn't want to overfill it either to avoid other costs. So we begin with the assumption that the production process is operating correctly and state the null hypothesis as mu is equal to 12 fluid ounces. The alternative hypothesis challenges the null hypothesis and state that mu is different than 12, which indicates either overfilling or underfilling is occurring. If the sample data support rejecting the null hypothesis in favor of the alternative one, then we can conclude the label is incorrect and underfilling or overfilling of the cans is occurring. If the sample data does not support rejecting the null hypothesis, then we conclude just that the assumption that the manufacturer production process is functioning properly cannot be rejected. Otherwise, we are not able to reject our null hypothesis. When we are not able to reject our null hypothesis, we cannot say that we have evidence that it is true either. We cannot say we have statistical evidence that the manufacturer production process is functioning properly. We can only say that the assumption the manufacturer's production process is functioning properly cannot be rejected. What are type 1 and type 2 errors? This is table 9.1 from your text. We haven't emphasized that the strength of our hypothesis test is to reject H0. And when H0 is rejected, we have statistical evidence to support HA. But when H0 is not rejected, we have no statistical evidence to support either HA nor H0. So the different conclusions that we can draw from our hypothesis test are actually do not reject H0 or reject H0. Also note that since H0 and HA are opposite of one another, stating HA is true is equivalent to stating H0 is not true. Now, if we accept H0 when H0 is true, then we've reached a correct conclusion. But if we were to accept H0 when H0 is not true, we would be reaching an incorrect conclusion or making a type 2 error. We would be accepting H0 when we should not because H0 is not true. In our previous pot roast example, type 2 error of accepting H0 when H0 is not true would correspond to stating that beef pot roast made by Morel is not the preferred choice, when in fact it is the preferred choice. So to avoid making a type 2 error, instead of accepting H0, we do not reject it. Next, if we reject H0 when H0 is not true, then we are reaching a correct conclusion again. But if we reject H0 when H0 is true, then we are reaching an incorrect conclusion, or we're making a type 1 error. We reject H0 when we shouldn't because H0 is true. In our previous pot roast example, type 1 error of rejecting H0 when H0 is true would correspond to claiming that the pot roast made by Morel is the preferred choice by more than 50% of the consumer population, when in fact it isn't. The probability of making a type 1 error, rejecting H0 when we shouldn't, is alpha, the level of significance. The person responsible for hypothesis tests specifies the level of significance. By selecting alpha, that person is controlling the probability of making a type 1 error. If alpha is set to 0.05, then the probability of rejecting H0 when it is true, when we shouldn't, is 0.5 or 5%. If alpha is set to 0.01, then the probability of rejecting H0 when it is true, when we shouldn't, rejecting it, is only 0.01 or 1%. So if the cost of making a type 1 error is high, small values of alpha are going to be preferred. So we can control for the probability of making a type 1 error, but not the probability of making a type 2 error. Not nearly as easily anyways. If we accept H0 when H0 is not true, we cannot determine how confident we can be with that decision. This is why we do not reject H0 instead. In doing so, we avoid making a type 2 error. Because we cannot determine how confident we can be accepting H0, by saying do not reject H0 instead, we are indicating we are holding judgment. That is why we say the strength of our hypothesis test is only in rejecting H0. This is also why when working with a research hypothesis, we first write our alternative hypothesis, the one we hope to support, the one we'll accept as the truth if we successfully reject H0. We'll be able to support our research or alternative hypothesis at the alpha level of significance, usually 5% or 1%. So we'll be able to support our research or alternative hypothesis with only a 5% or 1% probability of being wrong to do so, or making an error doing so. Now let's proceed with our hypothesis test. We go back to our manufacturer of soft drinks that claims its cans contain 12 fluid ounces. To check on this claim, we conduct a lower tail hypothesis test. The hypothesized value of the population mean is 12. When the population mean is the one hypothesized, then the mean of the sampling distribution, which is equal to the population mean, is also equal to 12. A sample of 36 cans of soda is selected. The sample mean X bar is computed as an estimate of the population mean mu. If the sample mean X bar is less than the hypothesized population mean 12, it will cast doubt on our null hypothesis that the population mean is equal to or greater than 12, and give support to our alternative hypothesis that the population mean is less than 12. The further down on the lower tail of our distribution the sample mean falls, the more confident we'll be rejecting our null hypothesis and accepting our alternative one. Now we know that because the sampling distribution of the sample mean is normally distributed, even when the true population mean equals 12, there are sample means that are going to have extremely low values, much lower than 12, and be in the far lower tail of the distribution. But by definition also of the normal distribution, these extremely low values are very few. So we are very unlikely to get such extremely low values for our sample means. In other words, a very low sample mean value casts doubt that such a sample mean was drawn from a population with mean 12. How low of a sample mean should we get before we consider it strong enough evidence to reject a null hypothesis and accept an alternative one? Well, we specify that ourselves by choosing the level of significance alpha. If we choose the level of significance to be 0.05 and the X bar values 1.645 standard error below mu equal 12 will be considered extremely low enough to cast doubt on our null hypothesis and give support to our alternative one. If we choose the level of significance to be 0.025 and any X bar value 1.96 standard error below mu equal 12 will be considered extreme enough to cast doubt on the null hypothesis and give support to our alternative one. If we choose the level of significance to be 0.005, any X bar value 2.576 standard error below mu equal 12 will be considered extreme enough to cast doubt on our null hypothesis and give support to our alternative one. As noted earlier, this level of significance corresponds to the probability of making a type 1 error, rejecting H0 when we shouldn't. Such extremely low X bar values are so very unlikely that they give us ground to reject H0, but such extremely low X bar values do exist. So we always have a risk of rejecting H0 when we shouldn't. And the probability of making such a type 1 error is equal to the probability that X bar will take such low values, which is alpha. Minus 1.645, minus 1.96, and minus 2.576 are called critical values. Let's say we choose the level of significance to be 0.05. Our critical value is minus 1.645. Assuming we know the value of the population standard deviation sigma, we compute the standard error of the mean. Let's say we get a sample mean of 10. How far below 12 is 10 units of standard error. If it is more than 1.645 standard error below the mean, we'll say it is extremely low enough that we have ground to reject H0. If it is less than 1.645 standard error below the mean, then we'll say it is not extremely low enough of a value to give us ground to reject H0. We find our z-value to be equal to -3, which is less than -1.645, so that gives us ground to reject H0. This is the critical value approach to determining whether or not we should reject H0. And so we compared our test statistic z to our critical value z.05 and decided to reject H0. Critical value minus z.05, excuse me. Notice that that critical value is the upper limit of the tail corresponding to the level of significance we chose. This means, alternatively, we can determine the p-value, or probability that x bar values are less than or equal to our z-value, and compare that directly to our level of significance. And this is the p-value approach. We find our p-value by using the table on the front cover of our text, or by using the norm_dist function in Excel, like we did in chapter 6. And whether we use the critical value or the p-value approach, we'll reach the same conclusion, and here we reject the null hypothesis. We just went over how to conduct a lower tail test and concluded that we can use either the p-value approach or the critical value approach to hypothesis testing. Both lead to the same result. The advantage of the p-value approach, though, over the critical value one is that the p-value tells us how significant the results are. That is why the p-value is also called the observed level of significance. For example, for a steady level of significance alpha equal 0.05, we might establish that our statistic z is less than our critical value, and based on that, reject H0. With this approach, all we know is that our result is significant at the stated level of significance alpha equal 0.05. Instead, if we rely on the p-value approach, we might establish that our p-value is less than our stated level of significance, and based on that, reject H0. With this approach, the advantage is we also know that our result is significant at the lower observed level of significance that our p-value is. Back to our soda example. Using the critical value approach, we reject H0 at the less stated level of significance 0.05. Using the p-value approach, we'll reject H0 at the observed level of significance 0.001. So we're able to establish that we are much more confident in rejecting H0. The probability of us making a type 1 error by rejecting H0 is actually only 0.001, which is much less than 0.05. This was a lower tail test. How about an upper tail test? Well, everything now is happening on the upper tail of the distribution. The only change to our rejection rules is the equality sign comparing our z statistics to our critical value. That changes direction since we are now looking at a positive value. Positive values. Let's consider a car that currently attains a fuel efficiency of 24 miles per gallon in city driving. Hypothesis test is used to determine whether a newly designed fuel injection system increases this car miles per gallon rating. So we hope to reject our null hypothesis to support that claim that the new fuel injection system increases the fuel efficiency of this car. A sample of 40 cars is selected. The sample mean x bar is computed as an estimate of the population mean mu. If the sample mean x bar is greater than the hypothesized population mean of 24, it will cast doubt on our null hypothesis that the population mean is equal to or less than 24, and give support to our alternative hypothesis that the population mean is greater than 24. The further up on the upper tail of our distribution the sample mean falls, the more confident we'll be rejecting our null hypothesis and accepting the alternative one. Now we know that because the sampling distribution of the sample mean is normally distributed, even when the true population mean equals 24, there are sample means that are going to have extremely high values, much higher than 24, and be in the far upper tail of the distribution. But by definition of the normal distribution again, these extremely high values are very few. So we are very unlikely to get such extremely high values for sample means. In other words, a very high sample mean value casts doubt that such a sample mean was drawn from a population with mean 24. Let's say we choose the level of significance to be 0.05. Our critical value is 1.645. Assuming we know the value of the population standard deviation sigma, we can compute the standard error of the mean. Let's say we get a sample mean of 26.4. How far above 24 is 26.4 in units of standard error. We find that our z-value is equal to 2.53, which is greater than 1.645, and that gives us ground to reject H0. Using the p-value approach, we are able to reject H0 at the observed level of significance, 0.006. So we are able to establish that we are much more confident in rejecting H0. The probability of us making a type 1 error by rejecting H0 is actually only 0.006, which is much less than 0.05. This was an upper tail test. How about a two-tail test? For a two-tail test, the level of significance alpha gets split in half between the lower tail and the upper tail. Here we've indicated that the critical z-value on the lower tail and upper tail have opposite signs. That's about it. The z-statistics would too, but we get only one of the z-statistic value, the one on the lower tail or the one on the upper tail. Otherwise, no change in our rejection rules. Reframing our soft drink can problem into a two-tail hypothesis test. So we set our null hypothesis as mu equal 12 fluid ounces to indicate that the production process is operating correctly. The alternative hypothesis challenges that, so mu different than 12, not equal to 12, indicating either overfilling or underfilling. A sample of 36 scans is selected. The sample mean is computed as an estimate of the population mean mu. If the sample mean x bar is greater than the hypothesized population mean 12, or if it is lower than the hypothesized population mean of 12, it will cast doubt on our null hypothesis that the population mean is equal to 12, and give support to our alternative hypothesis that the population mean is not equal to 12. The further up on the upper tail of our distribution, or the further down on the lower tail of our distribution, the sample mean falls, the more confident we'll be in rejecting our null hypothesis and accepting our alternative one. Now we know that because the sampling distribution of the sample mean is normally distributed, even when the true population mean equals 12, there are sample means that are going to be having extremely high values and sample means that are going to have extremely low values. So by definition of the normal distribution, these extremely high values and low values are very few, but they do exist. The fact that there are very few means that a very high or very low sample value is going to enable us to cast doubt or to doubt that the null hypothesis is true. We're going to use that as ground to reject our null hypothesis. because it is very unlikely to get such extremely high or extremely low value for our sample mean if the population mean is equal to 12. Let's choose the level of significance to be 0.10. So we split that in half, and this gives us 5% of all possible X bar values are found in the far left or far right of our distribution. If we get one of those values for our sample mean, it will be considered extreme or unlikely enough to warrant rejecting our null hypothesis, to justify rejecting our null hypothesis. At that level of significance for a two-tailed test, our critical values are minus 1.645 and 1.645. Assuming we know the value of the population standard deviation sigma, we can compute the standard error of the mean. Let's say we get a sample mean of 10. Our far from 12 is 10 in units of standard error. We find that our z value is equal to minus 3, which is less than minus 1.645, and that gives us ground to reject H naught. Using the p-value approach, we were able to reject H naught at the observed level of significance, 0.002. So we're able to establish we're much more confident in rejecting H naught compared to using a critical value approach. So the probability of us making a type 1 error by rejecting H naught is actually only 0.002, which is much less than 0.10. Note that for a two-tailed test, our stated level of significance alpha is the sum of the probability of X bar values being beyond our critical values on either side of our distribution, or twice the probability from one of the tail. Similarly, our observed level of significance, or p-value, is twice the probability of X bar values being beyond our z statistics values on one of the tail of our distribution. In this example, it was on the lower tail. In a different example, our z statistics value could have been found in the upper tail of the distribution. So this was the two-tailed hypothesis test. What is the relationship between this two-tailed hypothesis test and interval estimation? In Chapter 8, we constructed confidence interval estimates of a population mean. We pointed out that 1 minus alpha times 100% confidence level means 1 minus alpha times 100% of all the interval estimates constructed this way will contain the true population mean mu. For example, if alpha is 0.05, 1 minus alpha is 0.95, 0.95 times 100 is 95, so it's a 95% confidence level, which means 95% of all the interval estimates constructed this way will contain the true population mean mu. In other words, alpha times 100% of all the interval estimates will not contain mu. In our example, 5% of all the interval estimate will not contain mu. So if we reject H naught whenever the confidence interval does not contain mu naught, we will be rejecting the null hypothesis when it is actually true with probability alpha. So constructing a 1 minus alpha times 100% confidence interval and rejecting H naught whenever the interval does not contain mu naught is equivalent to conducting a two-tailed hypothesis test with alpha level of significance. So this concludes our discussion of hypothesis tests when the population standard deviation sigma is known. When the population standard deviation sigma is unknown, we end up with a t-distribution with n-1 degrees of freedom, like we did in Chapter 8. So we use our sample standard deviation to get an estimate of our sampling distribution standard error. And we have t critical values. and T statistic values instead of Z critical and Z statistic values. We find our p-values using table 2 in the appendix B of our text or by using T functions in Excel. Nothing else changes in the way we proceed to conduct the hypothesis test. On this slide, we have illustrated the rejection rules for a two-tailed hypothesis test when sigma is unknown. Finally, how about hypothesis test about a population proportion? In chapter 7, we said that if the following conditions are met, the sampling distribution of P bar can be approximated by a normal distribution. So the methods used to conduct a hypothesis test about a population proportion are the same ones as the one used to conduct a hypothesis test about a population mean. And this concludes our presentation on hypothesis tests.